Okay, about time to get started. I am wearing this headset tonight because I said that I was going to reserve time for questions, and it's quite difficult. It's probably impossible for me to hear someone who asks a question who's in the online group. So I almost have to have these on. And it would be really helpful if somebody online would say something like, "Yes, we hear you."
I can hear you.
Aha. I think maybe that was going over the speakers. Did you all hear something up here? Well, I guess that won't hurt. Okay, unless there's some special reason to do otherwise, if you're attending via Zoom, if you could turn on your video feed so I know who's actually here, that would be quite helpful. And I'm going to talk through the plan for tonight, and then I'm going to try to remember to switch the video. Right now, it's in the mosaic view, and if I forget to switch that back to emphasize the camera, then the recording turns out to be visually worthless. So if I don't know if anybody can detect that. I just better remember. Okay, so the plan for tonight is this. I want to make a couple of comments about the homework. And then I'm going to, that is the homework that was for last time. Then I'm going to make some comments on the next assignment. And then we're going to go to, probably I'll finish off this little bit of the last lecture. There was just a little bit left, and I'd like to finish that. And then I said I would reserve a significant amount of time for questions. And there is room in the schedule. So at that point, I can stop just lecturing. And if you have questions about the stuff we've been over, I'd be happy to address those. And then with the remaining time, we'll get started with the next section, which is 1.5 on linear transformations. And the good news is I think we can do the section 1.5 all in one class meeting. So even if our questions take up the whole time tonight, we'll be fine. We won't get off schedule. So let's get to it. And I've got to switch out to the camera here. And see if I can get this away from. Okay, that's better. Okay, just a couple of items on the turning in homework. First of all, if you are submitting your homework by email, and so then what you'll be doing is sending me some kind of a file, would you please put your name in the name of the file? Um, I know a lot of people, it's kind of natural to name it as it would make sense on your computer. So like if I were doing my homework, I might call it like assignment 1 or assignment 2 or something like that. The problem is I have a lot of people who are submitting files that say assignment 1 or assignment 2. So, if you put your name on there, like whatever, uh, Bill Jones, assignment number 2, or a date if you don't know the number, that'd be real helpful. It helps me avoid um, getting your stuff confused with someone else's. Um, and then whether you're submitting it physically or by file, if you'd please put your problems in order, um, and use white paper. Lined is fine. I don't have any problem with that. But for instance, I have a piece of blue paper here. I don't know how well that shows up online, but that tends to make kind of a distracting background. And sometimes it's the effects of the camera too. So I think this does not reveal anything about who submitted it. So for instance, this is something I got from someone, and in this particular case, I could read it, but quite often that a background that's other than white really, sometimes it can't quite figure out what it is I'm reading. So if you could use white paper and try to get your color balance, at least sort of kind of white when you scan, that'd be really helpful. Um, I didn't see much of this, but I have seen it in the past. So, if you do something like scratch out a half a page, that's probably a good reason to recopy that page. But, all of us, sooner or later, we make a mistake. We have to erase and mark out some small thing and start over. That's okay. But, just you don't so many pages of scratch outs, please. Um, as full size as you can do it. And I did want to kind of communicate here what I have in mind. Um, I have to be really careful because I don't want to show anybody's name. Now, here, oh, you can't catch the scale, but you can catch how incredibly well written this is. Um, on my paper, this is really small. And for most people, if I were writing it, it would be too small. But the point of this example is, it kind of depends on who's writing and how good their penmanship is. This one's extraordinary. It is small, but I have no difficulty reading it, so that's fine. But I don't want to spend a lot of time on your paper just trying to figure out what you were trying to write. So um, that's what I mean when I say please make it full size. Some scanning apps will do something like automatically compress the size of the page. So that's the reason I bring this up. It's not usually because someone is writing too small. So if yours is doing that, if you could adjust it so that when I print it out, I get a full page, that would be really helpful. And I think in general, that's probably all I have to say about standards for turning things in. Let me say a little bit, I don't really want to write this down, but in grading the first assignment, I was extremely liberal, I think. I made more than half of the points just making a reasonable attempt at each problem and turning it in. And I did that for a reason because, well, two reasons. Number one, you don't know me and you don't know what kind of things I'm going to be looking for. So I want to kind of ease you into that rather than, just um, uh, make it hard to be successful. And the other thing is probably, I haven't asked, but my guess is that quite a bit more than half of the class are not math majors. So different fields have different standards for writing. And so, I'm marking things on paper that I'm not necessarily taking off points for or taking a lot of points off for, because it's mostly I'm trying to be informative so that we can slowly kind of ramp up to the way that math professors do things. And by the way, if you ever have a question about that, I'm not, you know, if you send me an email and say, I'm not quite sure, did you want me to do this or that? Those kind of questions are fine. You're welcome to ask them. Next assignment. I am aware of the fact that the notes from last time are not yet posted to Blackboard. They should be later tonight. And I'm also aware of the fact that that last lesson was a pretty stiff dose of linear algebra. So I deliberately did not want to make an assignment due today because I wanted people to have a chance to sort of catch up and ask questions. On the other hand, if you, if you, once you get to where you have the bird's eye view on linear algebra, you see that we made so much progress last time. We pulled together a lot of threads that have sort of been floating around in the course. And having that done gives us some time to do the last few topics in linear algebra in a little more slowed down way. And I hope that that will be helpful. And I hope that when we do have time set aside for questions that you take advantage of those. So I will be posting what things I want you to turn in, hopefully tomorrow. And the notes from last time will be completed and will be posted tonight. So I hope that that will get you going. Now, just because I don't pick up papers on some week, that doesn't mean you should not do any homework. You know, if you took that strategy, you'd be behind and it would be probably pretty tough to catch up. So do be cautious about that. Okay. I think that's all I need to say about homework in general. Now, I want to make a couple of comments about some things that I noticed more than one person had trouble with. So let me talk first about row echelon form as opposed to row reduced echelon form and what we mean by back substitution. So for instance, this matrix, and I'm just picking this one out because it's in a form we can use. It wasn't the original. Actually, that's not quite there. This one will do. This is a matrix in row echelon form, not row reduced. Oh, it is row reduced. Shoot. Well, I may have to go to the homework set then. Okay. On problem number 6, or 5 rather, the instructions were to start with a system and use what's known as Gauss-Jordan elimination, which means to take it down to REF rather than RREF, and then use the technique of back substitution in order to solve the problem. So that would mean you take a matrix like this, probably plug it in your calculator because Octave doesn't have a nice command for REF. There are ways to get it, but not nearly so convenient as the calculator. So you enter this in the calculator and you choose the REF function rather than RREF, and you'll get this. And from here, you can solve the problem. So what I want to do is just copy this array out and then explain what we're looking at. And then we got 2 rows of zeros here. And by the way, I think this entry right here in the problem was a 6. And if you mistake that for a 0, then you end up with only 1 row of zeros instead of 2. And you end up with only 1 parameter instead of 2 at the end. So if you got tangled up on this, it's most likely because the original matrix was entered incorrectly. Okay, so these are the B's over here. And these columns relate to X1, X2, X3, X4, and X5. Now, a full solution, then we would, first of all, translate what this thing says. This one down here, notice we've got a 1 here in X4. So that's telling us that X4 is equal to 1. The next row up has its leading 1 in the X2 column. So this one doesn't tell us anything about X3. It does tell us about X2. X2 is equal to 0. That's the constant on the right-hand side. And then you subtract these terms from the other side. So minus X2 plus 2X3 plus 3X4 plus 9X5. And then likewise, X1 is equal to, it's got a 1 on the right-hand side, and then you subtract these other terms, minus 1/3 X2 plus 2/3 X3, and then a couple of 0 terms, so we don't really need those. All right, and then X3 and X5 are not represented in this matrix. So those are free choices or parameters. So probably we call this one S and this one T, although, you know, some people like to use A and B or something. That's fine. It doesn't matter. Okay, now, once I have this, I am now ready to start solving for my variables in reverse order. So X5, well, that's gone as far as we can go with it. It's T and there's nothing else to say. Same for X4, I have all the information I can get about that. That's fixed at 1. X3 is an S. And now X2, I've got that in terms of, whoops, how did I get an X2 over here? X3, I don't know. That's incorrect. 2X3 plus 3X4 plus 9X5. I think I was looking at that, but it's there. Okay, so now we're ready for X2. That is equal to 2 times X3, which we now know is S, plus 3 times X4. Well, we know that X4 is 1. And 9 times X5, and we know that X5 is T. So this simplifies to 3 plus 2S plus 9T, and then X1 is last of all. So we're working backwards through the list. That's 1 minus 1/3 x2. Well, x2 is this mess. Plus 2/3 x3, and x3 is s. And then, of course, you simplify all that. Now, the point of back substitution is this. Once you get a matrix into lower triangular form, which is the case here, that is everything below the main diagonal is 0, then you're going to have solved for your last variable, and you can use that to solve for the previous variable, then use those two to solve for the one before that, etc. You go backwards through the system, and that's why it's called back substitution. So when you see these instructions to either say Gauss-Jordan or row echelon form and back substitution, it means to do that process. And I think there's a simple one in here. Yeah, this one is had a unique solution. So row echelon form puts it in there. From here we can read that x3 is 3, and then we can take that 3 and plug it in for x3 here, which allows us to solve for x2. At that point, we know x3 and we know x2, and that allows us to plug those numbers into the equation we have for x1. And it's a bit of work, but you will find your way back to 2, and that gives us a solution. Okay, would anyone like to ask about that? Okay, now let me say a little about mathematical standards for answering questions, essentially. Essentially, if you come to a problem that says this, something logically equivalent to, is it true that, and then of course, that would be fill in the blank, you know, then the way that you answer those questions will depend on whether you think the answer is yes or no. If you think the answer is yes, then you need some kind of a proof, or you might say some kind of a general argument that the answer is indeed yes. Now, when I say general argument, I do not mean vague. What I mean is it applies to all cases. So if the answer is yes, a single example is insufficient. So let me give you an example of doing this incorrectly, and I'm going to do it in such a way that should be so you'll see why you don't want to argue that way. What if someone asks you this question? Suppose matrix A and B can be multiplied in either order. Is it true that AB equals BA? So, you know, I've got that style of a question. Is it true that for matrix multiplication, AB is equal to BA as long as both of those things are defined? Now, suppose you said yes. And let me just put a note in here. This is wrong. It actually is not true. AB times BA need not be equal even when they're defined. They need not be equal even when they're the same size. But, suppose you thought it was true and, you just made a mistake, we all do. And then you said, okay, so I'm going to prove it. And the way I'm going to prove it is I'm going to say, okay, take this example. And then I'm going to multiply it by this. Okay, if I multiply them this way, I get this product. Let's see, I'll get 2, 0, 0. Then I'll get 0, 4, 0. And if I multiply this column of zeros, I'm going to get zeros all the way down. And then you try the other way. Okay, well, it'd be 1 times the first column plus 0 times the other 2. It copies the first column. This says just double the middle column. And this says take 3 times the last column. And you look at that and you say, look, those are equal. Therefore, AB equals BA. I proved it. Now, you didn't. You didn't prove it. What you proved is that these two matrices, with these two matrices, A times B is the same as B times A, but this turns out to be an exceptional case. And so this is wrong. And a really easy example would be something like this. Well, how about 2, 0, 0, 3, and let me see, I would just like to make this not work. 1, 0, 0, 1. Actually, how about if I make this a 2? I think that will actually do it. So that would give 2, 0, and that'd give 4, 3. And if I turn them around, I'd get 2, 0, and I'd get 6, 3. And those are not equal. Oh, gee, I'm off the screen. Sorry. Those are not equal. So this example argument doesn't work because it only shows that these two matrices can be, you can reverse their order and you get the same thing when you take the product. But with these two, it fails. So a single example can never prove that it's true for every case. It can only prove that it's true for the particular single case you're looking at. On the other hand, if you read this original question here and said, suppose A and B can be multiplied in either order, is it true that AB equals BA? Then it would actually be correct to answer the question here by saying no, because here is an example, it didn't work. See, the formula is wrong if it's wrong for a single example. But in order for the formula to be correct, it has to be correct for all possible examples. So examples can be used to argue no, but they cannot be used to argue yes. Now, if you wanted to argue yes here, then you'd have to come up with some kind of a strategy to think about all possible matrices A times B that have the property that A times B and B times A are both defined. And it, even if you could, it wouldn't work because the claim is false. It is not true, wrong. They are not equal. And here's an example to show that this can fail. It won't necessarily fail every time, but you can't depend on it. That's the idea. Okay, so a yes answer requires a general argument. A no answer, a single example will do. Now, if you want to make a single general argument for a no answer, that's okay too. But it's usually quite a bit more work than giving an example. By the way, an example to show that something is false is, mathematicians usually call that a counter example. It means it's an example that goes against the thing that was claimed. Okay, now I want to give an example of this. In the homework, there was a question that said something like this. Suppose AB, these are matrices now, and BA are both defined. Show AB, that's a single matrix now, it's after you've multiplied them, and BA are both square. Now, it won't be good enough just to pick a couple examples, multiply them, turn them around, multiply them again, and say, aha, they're both square. Well, what you've done is proved it for a single case. So it isn't like what you said was wrong, it just wasn't enough. So here would be a full argument to make this case. You could say something like this. Suppose A is an M by N matrix. And usually then we'll just use some notation because we don't want to write this thing out every time. So we'll say something like denote by A M by N. Suppose B is, now I got to use some other letters because I can't assume anything to get started. I'm going to use S and T, but of course you could use whatever you wanted. S and T, so B is an S by T matrix, and we'll denote that by B S cross T. Now, I don't have very much to work with here other than this. AB is defined. And then, of course, I could say it the other way too. BA is defined. So AB is A. Now, this is an M by N matrix, and B is an S by T matrix. So, well, this tells me that this dimension and this dimension have to match, right? Otherwise, you can't do the calculation. So S must be equal to N. BA is defined. So BA, we could say this about it. It's B times, well, I could say S by T, but I already know that S is equal to N. So that's N by T. A is M by N. So, well, these two have to agree or you can't do the multiplication. So T must be equal to M. Therefore, A, and we have a notation for this now, A is M by N, and B is, well, S by T, but S is N, and T is M. Aha, so notice this. The dimensions of B are the same as the dimensions of A transpose. It switches the N and the M around. Okay, now I'm ready to multiply. Now, consider AB. Well, that is an M by N matrix multiplied by an N by M matrix. Well, these two agree, and the product AB is going to be an M by M. So AB is square. And a little bit of English doesn't hurt. Likewise, BA equals B. Well, we know that B is N by M, and A is M by N. And now the M's match so that BA is N by N, which is also square. And then there was a later question that says, well, if A, B, and BA are both defined, must A and B have the same dimensions? Well, once you've made this argument right here, and it's fairly lengthy for the first part, then when you get to that next question, must A and B be square? Answer, no. A is N by M, B is M by N, and M need not equal N. And then I think the question was, do AB and BA have the same size? And then if you wanted to, you could just refer back to your earlier work. No, BA is N by N and AB is M by M, and there's no requirement that M and N have the same size. Now on these, since the answers were no, some people in the homework just gave a specific example. They said, look at these two matrices, AB and BA are both defined, but they're not square, and AB and BA don't have the same size. That's fine, because the answer in that case was no. So you can give an example for the no answers, but for the yes answers, you do have to provide a general argument. I will scan this and put it in the notes for tonight. So I try to put some kind of a title on it so you know what I was talking about. Okay, does anybody want to ask a question about that? Okay. Well, I think that's all I had to say in general. So what I'd like to do now is to quickly finish up the last little bit of the lecture from last time, and then we will switch over to question and answer. Okay, last time we were working on the handout Introduction to Vector Spaces. We talked about what a vector space is and the difference between a subset of vectors from the vector space and a subspace of the vector space. And we did a bunch of stuff, and in particular, we talked about closure under scalar multiplication and vector addition. And then when it came time to actually make use of that, there was no time left. So the punchline to all of that is being able to prove whether a particular subset of vectors forms a vector space or not. in its own right. In other words, that it forms a subspace. So let me tell you about that, and then we will have that 1.4 wrapped up. Okay, first of all is the definition. A subset S of a vector space V is called a subspace of the vector space if it is a vector space in its own right under the same vector operations of addition and scalar multiplication as the big space. And you can prove that S, a subset of a vector space V, is also a subspace if it meets these two properties. It's closed under vector addition and it's closed under scalar multiplication. So maybe I will come back to these examples in just a minute, but let me give you some examples of things that, easy examples of subsets, that one that is a subspace and one that is not. So example one, I'm going to have a subset S of the vector space R3. R3 just means the vectors with 3 entries. Whether you write them horizontally or vertically doesn't matter. It's still R3. And I want, in this example, I want to show you one that is not a subspace. S equals, how about this? Anything for the first coordinate, anything for the second coordinate, but it's got to have a 1 for the z coordinate. That funny looking R means the real numbers. So any real number for first and second coordinate, but you have to use a 1 for the third coordinate. This is not a subspace of R3. And all I have to do is show that some property of vector spaces fails for this. Well, those two things that we said you have to test, closure under vector addition and closure under scalar multiplication, those are properties of a vector space. So if either one of those fails, it's definitely not a vector space. But there's other things you could check out too. For instance, it's got to have a 0 vector. If a vector is in there, its negative also has to be in there. And there's, you've got the various distributive laws and stuff like that. And I think this one is bad enough that virtually anything you test is going to fail. So let's try this. Let's just ask a simple question about it. Is this closed under scalar multiplication? Okay, so that would mean you pick a vector that's in the vector space or in the subset. We don't know if it's a vector space or not yet officially. And then you multiply it by a scalar and see if it has to stay in the set. Well, once you start thinking about the question, you probably already know the answer. Heck no, I can think of almost any scalar I pick is going to knock us outside of the set. About the only one that works is 1. So if I were writing a general proof, then I'd want to use things like this, xy and 1 or st and 1. But right now, I think it's going to fail. So remember, if the answer is no, one single counterexample is good enough. So let's pick one. It says you can do anything, right? So 2, 3, but here we're forced. Our hand is forced. That last one has to be a 1. And this element means, this symbol means 2, 3, 1 is an element of the set S. Or you could say, is in the set S. And now I pick a scalar. And let's give this a name, B. Let K equal 3, be a scalar. Then what's KV look like? Well, it's 3 times this vector, 2, 3, 1. And if I do the scalar multiplication, I get 2 times 3 is 6, 3 times 3 is 9, and 3 times 1 is 3. Oops, it jumped out of the space, right? Because to be in this set, that last component must be equal to a 1. Is not an element of S. So S is not closed under scalar multiplication. And S is not a subspace of R3. Now, if you check the notes, it gives you some other quick tests. If you think it's going to fail, some things to check. One thing to check is, well, if it is truly a subspace, then this is a vector space in its own right, and it's closed under scalar multiplication. So that means if you took any old vector and multiplied it by 0, you'd have to stay in the space, right? But any vector times the 0 scalar is the 0 vector. So the 0 vector has to be in the space. So there was really a way faster way to do this. It could have been this. 0, 0, 0 is not equal to xy1 for any xy. So the 0 vector is not an S, and S is not a subspace of R3. So this is an alternate to this. You don't have to do this and this. You could do this or this. So if you could just find a single rule that breaks, that's good enough to say no. To say yes, you got to prove all of them work, or quote a theorem, which gives you a shortcut. And our shortcut is this: if the subset is closed under scalar multiplication and vector addition, it is indeed a subspace. Okay, let me give you a quick example, an easy example that is a subspace. So draw a line there, totally new example. S equals, now I'm just going to modify the one I had before. The thing that was giving us trouble is if you multiplied, or for that matter, if you added a couple of these vectors, you're going to get something in that third component that's not a 1. However, 0 is a lot better behaved in that regard, right? If you take 0 times any scalar, it's still going to be 0. Or if you add a couple of zeros together, it's still going to be 0. So this one will work. xy0, xy in R. And this one I'm going to prove is a subspace of R3. So now, in this case, remember, back here, my answer was no. So I could give a single example that broke the rules. That's it. The answer is no. But now, if the answer is yes, I have to argue in general terms. I can't just give an example. So by the theorem that's on the opposite side of this page, by the theorem, S is a subspace if closed under vector addition and scalar multiplication. And the argument is pretty simple. So now I have to use letters. It isn't good enough to pick a single one or a couple of different vectors. I have to pick general ones. Let u be equal to, how about this? u1, u2, but the third component has to be 0 or it isn't an S. So I just notice that's an S. V be equal to V1, V2, 0. That's an S. And anything you pick in S can be fit into these formulas, right? Because all you got to do is force the last component to be 0. And let K be any scalar. All we have to do is show that K times U, or equivalently, K times V is back in the set, and we have to show that U plus V is back in the set. U plus V equals U1, U2, 0 plus V1, V2, 0 equals, well, the way we add vectors, we'll have U1 plus V1, comma, U2 plus V2. Now, if the UI and the VI are completely free choices, you can get anything you want there, right? But that doesn't matter because all those things are fine. Absolutely anything in the first two components, but 0 plus 0, you'll get a 0 here. That is back in S. How about this? Maybe I'll say V instead of U since V kind of reminds me of vectors. So K times V, what's that look like? Well, it's K times the vector V1, V2, 0, and that's equal to KV1, KV2, and it really doesn't matter what these are because absolutely anything is fine in the first two components, but this one matters. And it turns out to be exactly what we want. K times 0 is surely 0, right? And that's back in S. So S is closed under vector addition and scalar multiplication Therefore, S is a subspace of R3. And the whole proof just barely fits on one screen. And notice how this fits that pattern. If the answer is no, a single counterexample is good enough. If the answer is yes, you have to give some kind of a general argument. There is one other huge advantage to being able to write things like this, and that is the following. If you want to impress the other people at work, you leave a page of this sitting around on your desk. Most people in the population can't even begin to read it, and they will think you are a genius, even if what you wrote is completely wrong. So just a little tip I've picked up over the decades. Of course, if you've written complete slop and some mathematically informed person comes along, then it's a little embarrassing, right? But I suppose I should be clear. Yes, that was humor, in my opinion. Maybe it wasn't funny to you. Okay, any question about that? All right, I have now given you examples of this. Let S be a subset of a vector space V. S is a subspace of V if it's closed under a vector addition and also closed under scalar multiplication. You have to prove both of those to conclude that it's a subspace. Some examples. Well, gee, this one looks familiar. Everything of the form AB0 is indeed a subspace of R3. This sort of thing will work too, A2A3A. And if you just think about it for a minute, suppose you added that to B, 2B, 3B, you could factor the 2's and the 3's off and the pattern is preserved. And like, is the zero vector in there? Absolutely. Set A equal to 0. You get zeros all the way across, right? So everything works out very nicely for those. Upper triangular matrices turn out to be a subspace of the vector space of all matrices of that particular size. Upper triangular just means this. You have a main diagonal in the matrix, and upper triangular means you can have absolutely anything you want on the diagonal and above it, but below the diagonal, you're forced to have zeros. That's upper triangular. And of course, you could flip it around and that'd be lower triangular. If you have the stuff on the diagonal and below, with zeros above, then that's a lower triangular matrix. Symmetric matrices, those turn out to be a subspace of the vector space of all n by n matrices. That means matrices that have this property, the transpose of the matrix is equal to the matrix itself. Diagonal matrices, those are subspaces. That means non-zero entries only on the diagonal. Off the diagonal, either side have to be 0. Or how about this? You'll like this. The subset consisting of the single matrix with all zeros in it. That is, in fact, a subspace of the vector space of all n by n matrices. Why? Well, if you add it to itself, you get back to itself. And if you multiply itself by any scalar, you stay right there with itself. It's not a very interesting subspace, but it is indeed a subspace. So those are all possible. Things that aren't subspaces, vectors with positive entries. Well, what happens when you multiply it by -1, right? It bounces you out of the set. Vectors where the x-coordinate is a sine of some t and the y-coordinate is the cosine of the same t. Well, no. Notice, for instance, sine t equals cosine t is never true if either the sine or the cosine is equal to 0. So you can't have the 0 vector in there. Or how about this? 0, 1 is in there, but if you add it to itself, you get 0, 2, and the cosine never gets up to 2. So it's not closed. Okay, some quick tests, which I have already mentioned, but I'll mention again. To prove it is a vector space, you got to prove the two closure properties. But to prove it's not a vector space, it's sufficient to show it doesn't have a 0 vector. There is a single vector v for which -v is not in the space. If v is in the space, -v has to be. That's a special case of scalar multiplication, right? It's v times -1. So if v is in the space, -v has to be in the space. If that's not true, it's not a subspace. Or if it fails on either the closure properties. Negatives and the 0 vector are good things to check if your intuition is, hey, I think this is probably not a vector, is not a subspace. Check for the 0 vector, check that negatives are in there. If it passes those, well, you're gonna have to work harder. And these are some examples I thought of ahead of time, but I've actually already done a couple examples, so maybe I'll let those go for now. And that's work coming up. Okay, so that finishes the 1.4 notes. And that means we have an hour available for answering questions. So the first really big question is, can I put the paper clip on? Yes, I did it. Not very elegantly, but it got done. Okay, would anybody like to ask a question? Sam. Yes. So I'm sure if you're attending by Zoom, you probably couldn't hear the question. The question is this, just briefly, what is a basis of a vector space? And there are some questions in homework that sort of talk about a simplified version of a basis or something like that. What's the whole point of that? So a basis, let's answer this question first. It is a linearly independent spanning set of vectors in V. Now that's the official definition, and it works absolutely wonderful if you already know what it's supposed to say. But usually mathematical definitions they're deliberately terse. So if you're having a little struggle with them, just repeating it usually doesn't help. So let me give you a couple examples of bases for, let's say, R3, because it's a vector space we're familiar with. And in the context, I'll talk about, there's two conditions here. One, it's got to be linearly independent. Two, it's got to span the whole space, okay? So let's start with the standard basis for R3. Since it's the standard basis, I'm giving it away in the name, right? This is in fact a basis. Now, what does linearly independent mean? Well, in this case, well, in every case, it means this. These actually have standard names, so let's do it. Their standard names are E1, E2, and E3. And if we were in 5-dimensional space, they'd be similar things, E1, E2, E3, E4, E5. So these are the standard basis vectors. Linearly independent means this. If you take a constant times the first vector, excuse me, plus an arbitrary constant times the second vector, plus an arbitrary constant times the third vector, set that equal to the 0 vector, that forces each one of the constants to be equal to 0. In other words, now, of course, we know no matter what these vectors are, if you set each of the constants to 0, you're going to add up to the 0 vector, right? But to say linearly independent means that's the only way to get the 0 vector. There isn't a second way. So in this case, because these are so simple, it's pretty easy to see that, because the sum of these three terms here, well, you'll get C1 times 1 in that first component, and those are just zeros. So you end up with this, right, in the top, the first component of the sum. And you'd end up with this one in the second and this one in the third. Now, I say that like it's completely obvious, but it's obvious because I've done it a bazillion times. It's obvious to me because I've done it so many times. But is that clear? C1 times 1, and then I'm going to pick up zeros, so this sum is going to have a C1 in it. And then likewise C2 in the second and C3 in the third. And I'm setting that, I'm not hoping it comes out that way, I'm setting it equal to 0. So this does, in fact, force C1 to be 0. It forces C2 to be 0, and it forces C3 to be 0. Make sense? Now, let me give you an example of a set that is not linearly independent, okay? So how about this one? New set, that was S, we'll call this one T. T, I'm gonna do my best to make this really simple, because if we had to calculate for 20 minutes, it wouldn't be probably very helpful as an example. And this, I'm gonna leave this at 0 here. Doesn't matter what I put up there, it's gonna be linearly independent. So I'm gonna call this one 1, 2. I think I said independent when I meant dependent. This will be dependent. That is not independent. How do I know that? Well, let's take this linear combination. I'm going to take 1 times the first vector, 2 times the second vector, and minus 1 times the third vector. What do those add up to? Well, I get 1 plus 0 minus, wrong. And now I'm trying to erase my ink pen. It's not going to work. Minus 1 times, I got ahead of myself. 1, 2, 0. And it is indeed equal to 0, 0, 0, but I wasn't ready to write that before. Okay, try again. 1 plus 0 minus 1 is 0. 0 plus 2 minus 2 is 0. 0 plus 0 minus 0 is 0. Aha. So this linear combination, coefficients 1, 2, and minus 1 on these will sum up to be 0. And then, of course, I mean, this is always true. If I multiply the first one by 0 and the second one by 0 and the third one by 0 and add them up, well, magically, it happens to come out to be 0, right? But the point is, I've got 2 different linear combinations that add up to 0. That's disallowed. And the term dependent means, you could think of it this way. This vector could be built out of these 2. You take 1 times this plus 2 times this, you get that, right? So that means this depends on those, and that's why we call the set dependent. Okay, so that's the first part. What's a basis? It's a linearly independent spanning set. Now, span is the next thing. I was trying to do what we used to do with those roll-up acetate things, which you've never seen because you're too young. It's just not going to work. Spanning means this. Let's take that first one. We had this. these three vectors, the standard basis vectors, they span the whole space. And what that means is this. Suppose you want to ask the question, well, let's just pick something specific. How about the vector 1, 2, 0? Can I build that out of these? Well, sure I can. It's 1 times this plus 2 times this plus 0 times this will give 1, 2, 0, right? As a matter of fact, it doesn't matter what you pick over here. I can find a way to build a linear combination of these three that will add up to what you want. So in other words, if let's make it look like a system of linear equations, pick some numbers, B1, B2, and B3. Can I solve this? Can I find X, Y, and Z that will make this true? And the answer is yes. Set X equal to B1, Y equal to B2, Z equal to B3. This is solvable. Let me give that a name. The vector B. For any B in R3. And that's what we mean, i.e., these three vectors, E1, E2, E3, span R3. You can reach anything in R3 by taking linear combinations of these three vectors. Does that make sense? Okay, now let's go back to the second example I gave, T. I think I did this, 1, 0, 0, 0, 1, 0, and what do I have, 1, 2, 0? I think that was it. This does not span R3. How do I know that? Well, I can pick a vector in R3 that cannot be built with linear combinations of these. For instance, X times 1, 0, 0 plus Y times 0, 1, 0 plus Z times 1, 2, 0. It's actually really easy to pick one because you'll notice the third component here is always 0. So if I pick something that doesn't have a 0 there, doesn't matter how I fill these in, it can't be solved, right? So how about 115? There's no solution. In other words, the vector 115 is outside. To use colloquial words, it's outside of the reach of these vectors. You cannot get to here by taking linear combinations of those. So the official word for it is span. So it's outside of the span of that set T. So to say that a set of vectors in a vector space is a basis means this. First of all, it's linearly independent. You don't have any dependencies in the set. There isn't one in there that you could build out of the others. Number two, you can reach absolutely anything in the vector space by taking linear combinations. So there's no redundancies, and you can reach out to the entire space. It's a linearly independent spanning set of the vector space. Did it help? Which I'm not sure I'm with you. Which problem is this? Okay, find a basis for the null space, the column space, and the row space. That's the one? Okay. Oh, okay. Okay. It's way easier. Okay. When I show you an answer, let me do one for you. All right. And then when you see it, you'll think, oh, that was too easy. So we need to enter a matrix here. Why don't we work off this guy? Because it's big enough that it's something to do, but it's small enough we can enter it pretty quickly. So, and I'm using the calculator because I can show it on the screen easily. So 1, 0, 2, 2, 2, 6, 0, 2, 2. Okay, now if you're not me, you can skip this step, but I have so many times made a mistake entering the thing, and then I do 30 minutes worth of work and nothing's working out right, only to find out I put the wrong data in, you know. So I've found it a good idea just to double check. Okay, now let's take the row space, because that one is really straightforward. So my matrix so we want to say what the row space of A is, where A is this matrix 102, 226, 022. Well, first of all, you have to know what the row space is. The row space of A is equal to the span of the rows of A. In other words, it's the set of all possible linear combinations of this row, and this row, taking those to be vectors, individual vectors, okay? Now, if you just look, especially if the matrix is large, and this one's probably complicated enough, it isn't obvious right at first, right? I don't know if for you, but for me, I look at that and I think, you know, I'm not sure. I wouldn't be surprised if it's all of R3, but I'm not absolutely sure. So there's a theorem that tells me this: the row operations, elementary row operations, do not change the span of the rows of a matrix. So officially, the row space of A is the span, that is the set of all linear combinations of these three vectors, 1, 0, 2. And by the way, this is true but useless. All right. So I'm writing it down. It's a true statement, but it's so complicated that probably most of us don't have a lot of intuition about what it is. So what's the row space of A? It's the span of those. Gee, I wonder if I could think of three vectors that I could use instead of these that are simpler. Answer: yes. Take the row reduced echelon form of A and work with those, because that's what the theorem says. The span of the rows is not changed by elementary row operations. And how do you get the row reduced echelon form? By a sequence of elementary row operations. So that sequence will not change the span of the rows. So what I'm going to do now is, in my calculator, I'm going to go to RREF A, and now I have a simpler set of vectors to work with. So this span is the same as this span. Now, at this point, I would say this set is obviously dependent. You know, can you build 0 out of those two? Yes. Take 0 times this plus 0 times this, it'll add up to 0, right? So this thing is useless. It's adding nothing to the span, whatever. You may as well ignore that. So that is going to be the same as the span of these two. And this is always true. You can, if you have the RREF, the row space is the span of the non-zero rows. You can always throw away the 0 rows. And then you just think, well, what do all possible linear combinations of this look like? Well, it'd be some scalar, let's say A, times the first, plus some scalar, let's say B, times the second. And what's that add up to? Well, I get A here and nothing else. In the middle, I get B. And at the third component, oh, I'm off the screen. Sorry. I get 2A plus 1B. A, B are any real numbers. Now at this point, I have a pretty good idea of what's in there and what's not. You can take the first two components are free choices, but once you have made those choices, the third one is fixed. You take twice the first plus 1 times the second to give you the third component. This is the column space, or rather the row space. And of course, if you're going to write it that way, then this should be a set, and that should be a set, and all that. But does that help? Okay. Yes. Oh, yes. S and T, things like that is fine. Okay, so now let's suppose we want the null space of this matrix. So the null space is the set of vectors V, or maybe we're sort of used to writing it this way. Maybe I should say it X. It's the set of vectors X that have this property. A times X is the 0 vector. So it means we're going to solve this homogeneous system of equations. And the way we'll do that is to row reduce. Now, lucky for us, if you just stick a column of zeros out here on the right-hand side and row reduce it, you're always just going to have zeros there. So the row reduced echelon form, this is row equivalent to this. We've already done the RREF, 102, 011, and 3 zeros. So this says that X1, we're going to get a solution for that. X2, we're going to get a solution for that. X3 is a free choice. And if you use like S and T, that's fine. A and B is fine, doesn't matter. So I'm going to go with S here. So this says that X2 is equal to, now the right-hand sides are all 0. It's 0 minus X3, which is minus S, and X1 is 0 minus 2 times S. So now we convert this to vector form. So the solutions to the homogeneous system are these vectors X. They have this form, S times minus 2, minus 1, 1. So in essence, the Null space is the span of a single vector. Yeah, if you want to write this in formal notation now, it would look like this. Null space of A is equal to a set of vectors where S is any real number. And what I had before, the row space of A, it's equal to, I gotta look it up now. Where'd I put it? Well, it doesn't matter. I had it on my screen. It's the span of these two vectors. So you could write it that way. The span of these two vectors. Or if you prefer, you could write it in a more parametric form. Like so. Did that take care of that question? Yes. No. There's the null space of the transpose of A, and there's the null space of A. Now, it turns out that if you're doing a little more theoretical linear algebra than we're going to get to, this is important. But for us, we're just going to be paying attention to this. Since I've addressed this one question, all but one point, let me address this point. Well, so what do you do then if you need a basis for the column space of A? Well, if we had in our calculator a function that would column reduce the matrix in addition to row reduce the matrix, well, it'd be what? Like the CREF, the column reduced echelon form. We'd choose that function and boom, we'd be done. But we don't have any such function. So what you do is you take the RREF of A transpose, and then once again, you read the rows. Or if you don't like that, reading the rows when you're looking for a column space, what you do is you start with A to write the notation, then you take its transpose, then you compute its RREF. Now at that point, you've got a matrix, right? And then you take the transpose back, and then you read the columns. But all this last transpose is going to do for you is allow you to read columns rather than rows. So I think it's kind of a waste of time. But if you like it, and some people do, you know, it's kind of a style question, then go ahead and do it. There's nothing wrong with that. Just keep track of whether you're supposed to be reading rows or columns. Okay, so I think that pretty well takes care of that one question, number 12, because it's asking you to compute the null space, the row space, and the column space, right? And by computing, it means give a basis or explain what the, in some mathematical way, what's in there. Okay, I think I should, it would be so easy for me to ignore everybody who's in class online, and just out of convenience, you know, it's harder to communicate with you. So let me just quickly switch back to this format. Do any of you want to pose a question? We've got 30 minutes left, so.
I have a question.
Yeah.
I was wondering if you were saying earlier how you can add or subtract 0 rows from certain matrices, and I was wondering if there are any functions where that doesn't work, or if there are certain places where that's useful.
Could you give me a little more context? I'm not really quite sure what you had in mind.
Well, I was just messing around in my calculator and doing some multiplication of matrices. And if you're given a matrix that does not have compatible dimensions, like you wouldn't normally be able to multiply it, would it be appropriate just to add an extra 0 row? Can you technically do that, or is that not?
Okay, that's a good, clear question. So let me repeat it for the people in the physical classroom. I don't think you could hear it, could you? The question was this: suppose I wanted to multiply two matrices, and the row or column counts were off, so the multiplication is not defined. Would it be okay to sort of pad one of them out by adding some rows or columns of zeros and then proceeding to do the multiplication? I think that's a fair restatement of your question. The answer is no. If you have A times B, if you have A and B and you're trying to multiply them and the dimensions don't match, then you just simply say that A times B is not defined. Okay. Now, might there ever be some situations, some application of linear algebra where it would make sense to fix them up so they could be multiplied? Well, yeah, maybe. But I don't know of one right offhand. But as it turns out, I don't know everything. So it's probably a terrible shock for you, right? Okay. Did I answer the question?
Yeah, there was an earlier problem where I believe subtracted a 0 row, so I was kind of confused as to when that is allowed.
Okay. So there was an earlier problem in which a 0 row was thrown away or ignored or something like that. So when are you allowed to do that? When in the problem we just did, where I was computing row and column spaces, there was an example. Let me switch back to my document camera. In this example right here, for instance, let me see. Yeah, we're trying to, that's the null space. It's in the row space. Looks like I tore the row space off. There it is. You start with this matrix here, and I'm in the wrong view. You start with this matrix here, and you row reduce it, and I don't have that on the page, but I do have it on the calculator. You happen to get this matrix. And I said the row space is the span of this row and this row. It is safe to ignore the row of zeros. That is, that's because we sort of moved beyond the matrix at that point. We're reading the rows off as vectors, 102, 011, and 000, and then we're looking at the span. And the zero vector never expands the span of any set, because no matter what you multiply it by and add it to the sum, you've done nothing, right? You haven't you've neither increased nor decreased the sum. So the short answer is the reason you could do it here is because we're interested in the separate rows as vectors as opposed to the whole assembly as a matrix. Does that answer it? Okay. All right. From either group, do we have another question? By the way, if you're attending online and I'm missing you, you can always type a message like I have a question in the chat too. That's fine. Tommaso. Oh, okay. To restate the question, does the determinant tell us anything else about a matrix other than you can use it to solve systems of equations rather inefficiently with Kramer's rule? The short answer is this. In general, in the general linear algebra setting, the determinant does tell us something useful, but it's sort of a 0 or 1 kind of answer. It isn't the size of the determinant. If the determinant is 0, then the if the determinant is 0, then either the rows or the columns of the matrix are linearly dependent. So that matrix, even if it's square, does not have an inverse. And if it's anything other than 0, it does have an inverse. Actually, I was so careful how I stated that. It doesn't even have a determinant if it's not square. So I can stop hedging on that point. Only square matrices have determinants. If the determinant is non-zero, the matrix is invertible. If the determinant is 0, it's not invertible. And another way of saying that would be if you were to compute its row reduced echelon form and the determinant was 0, you must have at least one row of zeros, maybe more, but at least one. And in the same way, you'd have, if you took its transpose and row reduced, you'd produce a row of zeros in that, equivalently a column of zeros, if you column reduced it. Now that, once you land on that, it does or it does not have an inverse, you're into the situation with where the invertible matrix theorem applies. So once you know that a matrix is or is not invertible, there's a whole list of things you know about it. Yeah, it's quick if the matrix is small and you have a calculating machine. But in reality, determinants are very messy to compute, and they're computationally intensive. In like engineering situations, you'd be much better off row reducing the matrix than computing the determinant. At least computing the determinant in a naive way, which is, from the definition or something. You don't want to do that. Okay, let me look back to my online half of the class. Any questions from you all? Okay, anybody in the classroom have another question? Yeah.
talking about it, but I didn't really connect the dots as to
This is actually something you're going to see over and over again when we're solving linear differential equations. And this is a particular solution in that case, and the solution to the homogeneous equation. Now, with systems of linear equations, such as we're doing right now, this thing still applies. And it would be easiest if I give an example, probably. And I'm going to give it in row reduced echelon form just so that I can get to the essence of what I want here quickly. How about this? Suppose after we row reduce, we end up with this. Okay. So these are the right-hand sides, the B's over here. And this column corresponds with X1, with X2, and with X3. And you can see because this is the coefficient matrix, since we row reduce that, we got a row of zeros, its determinant would be 0, which is the same as saying this is a non-invertible matrix. And if you go back and look at the invertible matrix theorem, which by the way, you all should do now, because at this point, you're finally seeing enough that it should begin to make some sense. The first time you saw it, it was probably like, okay, whatever. But after you work with this stuff for a while, you begin to realize how valuable it is. Since I see that row of zeros in there, that tells me there will not be a unique solution. There'll be infinitely many. And now I'm ready to start working with that. Okay, so let me write down the full solution set here. And then I'm also going to write down the full solution set for the homogeneous system, the one if you just started with all zeros on the right-hand side. Okay, so this is the equation. This is solving AX equals B. And later I'm going to discuss the solution of AX equals 0. So for right now, it's just the usual kind of stuff. X1 equals 3 minus 2 X3, but of course X3, I'm going to give a name to that, S or T. I'll call it T because I write T's better than S's. X2, it's equal to 4 plus 1 times T, and then X3 is equal to just plain old T. Okay, so let's write this in vector form. X is equal to 3, 4, 0 plus T times minus 2, 1, and there's a coefficient of 1 here. It doesn't quite line up, but if you slid that over, you could just see the vector. Okay, and that's all solutions of AX equals B. Now, what if we had solved instead the homogeneous equation? Well, in that case, I would have started with A here. I'd have zeros in the right-hand column. And when I row reduced, well, everything on the left, it'd still be the same. So of course, I would still get this. The difference is that I would have 3 zeros here. So what does the solution of the homogeneous system look like? Well, this says X1 equals, now you've got 0 minus 2t. X2, X2 equals 0 plus 2t. Oh, hold on. I copied it wrong. That's supposed to be a minus 1. And X3 is equal to t. So in this case, the solution in vector form is this: minus 2, minus 1, 1 times t. Forgot my parameter. Okay, now what I am trying to say there is, look, these things match. And what is that? That is the set of all solutions of the homogeneous equation. And what's this? This vector by itself, it's some solution of the non-homogeneous equation, yp, a particular solution. So for instance, if I just try that, 3, 4, and 0, does it work? 3 plus 0 is indeed 3. 0 plus 4 plus 0 is 4, and those add up to 0 again. So this is some particular solution. It's really, it could be anything that solves this one, plus the set of solutions to the homogeneous equation. So it always fits this pattern. A particular solution and so it's one, not many, just any one, and all solutions of the homogeneous equation AX equals 0. And sure enough, in this case, it's easy to see that that works. Now, what we haven't done with the theory yet, but I'll just tell you it's true. It absolutely does not matter which particular solution you put in here. So for instance, if I set t equal to 1, another particular solution is this. 3 minus 2 is 1, 4 plus 1, 5, 0 plus 1 is 1. Those are the same set exactly. And if you think, oh, wait a minute, they sure don't look the same. Well, think about it. Maybe if I give this a different name, call it S. If I were to subtract this out of this, I would get that, right? I could be careful here. This could be impolite. If I subtract this out of this, I get that. So if I made S equal to t minus 1, I think that's what I want. Yeah, then it would subtract one of those t's out of this, and I would end up with the same thing. So the span here and the span here are the same, is the point. So it doesn't matter which one you pick, any particular solution plus all possible solutions of the homogeneous equation. Oh, yeah. By the way, there's a related thing here. It's not exactly this question, but it's worth commenting on. Let's just take this one right here. The set of solutions to the homogeneous equation is this set. You could just as well have said this. What really matters, why? Because let's suppose I chose a 5 here to get a vector. Well, I choose minus 5 here and I'll get the same vector, right? So you could multiply all of these by anything non-zero, or divide all of them by anything non-zero, and you get an equivalent set. So maybe for who knows whatever reason, just because I'm eccentric, I really like having a leading 1 in all my vectors. Would this be the same set? Yes, it is. I've multiplied this by a non-zero constant. So that's fine. Yeah, it's exactly what it is. And think about it, you're taking all constant multiples, right? So if this is proportional to that, it'll be fine, because you can just change it up by using a different constant. Yeah. Gosh, you all ask good questions. Some groups I get questions like this. Well, is this really going to be on the test? By the way, I have an answer. I learned it. I was still a shiny young assistant professor. It's really just a trick to stop that question. What I do is I look thoughtful for a moment and then I say, that is an excellent idea. Yes, that will be on the exam. After that, no one asks. Unless they're particularly slow group. They might ask twice. You all are too smart for that, though. Okay, any other questions? Okay, if I didn't get a homework assignment from you earlier, and you really are serious about being in this class, you should contact me. But you'll know whether I got it in one of two ways. Number one, if I recognize that I didn't get one, I will send you a private message just now. And if you don't get, if you don't get it back, then that would also be an indicator I didn't get it, right? Because they're almost all graded now. I have just, I think like maybe 3 papers left to go. And I'll be scanning. If you submit that by email, I will scan the paper and send you back the scan. Okay. All right. So unless there are other questions, I guess we're done. And we will take up the linear transformations in the next class on Thursday. And you can expect the next handed homework assignment to be posted to Blackboard soon. I mean, coming out of these things you've just been working on. So you'll know which ones to write up and hand in. All right. Good night to you all. No, I'm gonna make it due on this coming a week from today. And it was just so after some soul searching, I thought, you know, what if somebody in here is working 60 hours a week and the only time they have to work on it is the weekend? Well, I don't want to cut them out. So by giving you a full week, then no matter what your weekly cycle looks like, I hit that time so you can get your stuff done. Not right now. No, no. Okay. Good night. I wish you well. Yeah, yeah. That's the way it always used to be. Oh, you're so welcome. I hope it helps.
Yeah, definitely. It's, good insights.
Hey, Professor.
Good night. I'm working on this, Jack. I just got to get to where I can type. Yes, is the answer. The next homework will be due a week from today. I will be posting which things to hand in within the next day or two. And I have almost finished with the grading of the first one. And when it's done, I will scan it so you get to see my remarks and send it back to you. And hopefully at some point I'll get the grade book for Blackboard working as well, which will give you a confirmation. But if, by the way, is ever any question, did you get my homework? When should I expect to get it back? Something like that. You're always free to ask. Okay. Okay, I'm ready to sign off unless I get a message from somebody that I shouldn't. All right, good night.